Thank you, Arun. A very good morning to your friends and colleagues, and my very old friend, my classmate, Dr. Niyogi. He is, of course, Canadian now. And I feel very happy to come to the department and give a seminar, because I gave a seminar here exactly 10 years back, in 2005 summer, I think. It was a different seminar hall at that time.
Right.
And I also find it extremely pleasant experience for me to be back to this campus, because though my major connection outside India is Germany, and I have spent many years in Aachen. I don't know if any one of you are familiar with the city of Aachen. It's the border of Belgium, Poland, and Germany. And sitting in Professor Mishra's room, I was finding as if I am sitting in my office in Aachen, because they also have a gym exactly like this, called Loosberg, and the buildings, etc., they look exactly as it is in Germany, that particular part of Germany. So I find it very nostalgic, though I have been coming to this city since 1993, Roy, isn't it? And it is always a very pleasant experience. Thank you very much for coming, braving the rain we have. But perhaps this rain is also useful, because in Germany they call it Arbeitswetter. That means you cannot do anything else but work and listen to some boring lectures. So I think what I will do today, before I start my talk, I would like to explain that how this talk I organized, and actually this is based on a full science selective course I used to offer in IIT Kanpur, which was a very popular science selective among all students of engineering and science. So before that, I will tell that actually I joined teaching profession as a lecturer in 1965 May, a little more than 50 years back. So I taught at a place which was also my alma mater, where I am again working. It is a 160-year-old institution, and you can see some parts of the institution, not the central thing, of course, that is Victoria Memorial, you know. And after teaching there for 5 years, I was leaving for IIT Kanpur, where I spent, this is same institute with where I am now, the IIST Shivpur, that is the old campus. It's a very 200-year-old campus, almost like yours. And this is on the bank of River Ganges, where if you are too tired, you can go to the bank of Ganges, and this is the view from that. And this is the place where I shifted and I worked for 38 years. I come in between. I came to IIT Kharagpur also, of course. There is a building also shown here that belongs to IIT Kharagpur. IIT Kharagpur, sorry. This is the main building of IIT Kharagpur, and Professor Mishra knows it very well. And this is IIT Kanpur, you can see. This is the classrooms of IIT Kanpur.
Are you okay with that?
Do you want to switch off the light? Laser pointers are always like that.
Yeah. Yeah, you have to. Right. It is not no problem.
So I think what happens in main story comes now, that from my childhood I was extremely fond of eggs, you know. And I used to tell my mother I want to take 3 eggs at a time, egg curry. And she will never give me more than one, that you will get stomach problem, etc. Of course, my mother is gone, and I have grown up. But things have not changed, because my wife will not allow me to take more eggs, not more than 2 per week. So situation is a little bit worse now. So anyhow, I used to think that when I will grow up, I will be independent, I will take as many eggs I want at a time. So the night I was waiting to leave my campus, where I spent 12 years as a student and as a teacher, to 1,000 kilometers away place, Kanpur, IIT. So my household belongings were taken away by my wife to my native place. I was alone. So I never cooked it, not even a cup of tea, because I never came to USA for my studies. Otherwise, I would have been essential. And so what I did, I thought today I will make egg curry myself, and I will eat at least 3 eggs at a time. So I went to the market and purchased 3 eggs, and I brought home. I knew that you have to boil the egg at least. So I boiled, peeled off the skin, and then I was ready to cook. I thought what to do. I said, what are cook normally? Some turmeric, some oil, and some salt. I mixed up something, boiled it, and I prepared some little bread. When I tried to eat, it was impossible. I could not even touch it. It was tasting like soap water. Then the revelation is that since last 29, 30 years, I am eating eggs, liking it, consuming it, and also digesting it, but I don't know how to cook egg curry. So then I thought our education system, by and large, what we teach our students as science is a cooked science. But we never tell them how the science was cooked. So when they become budding scientists, like my young friend, he is in school, but he will join Cornell next year. So he will be a scientist, and of course he has to know how to cook science, and that can never be done if you all the time are busy with consuming food science. And that is what I realized, though the connections are not very definite, but I think at least my senior colleague teachers will agree that just teaching the formulae and something which is well-framed subject does not help the students to become good scientists, where they will have to independently bring out new science. So that's how we started teaching this course. And I come to conceptual evolution of mechanics. Since I work in the area of mechanics, my previous seminar here 10 years back was also on mechanics. There I proposed certain modifications of Newton's laws and how things can be explained. But anyhow, today actually I wanted to bring to you whatever I have studied during the last couple of decades, and consolidate the whole thing, that how the whole classical mechanics or other Newtonian mechanics evolved. It is not exactly, I am not going to present the history. History of mechanics is, there are many wonderful books. My point will be to really touch upon the conceptual transition happenings, what concept gave to what and how concepts are born. That will be more important rather than presenting the chronology of the whole thing. Now, why this topic? There are so many other branches of science. Because Newtonian mechanics is also often referred to as dynamics, and that is science of motion. And it is the most fundamental of all physical sciences and forms the foundation for almost all topics of physical and engineering science subjects. That we all agree is the most basic science subject. That's why we bring our students in contact with this subject at the very early stage. Maybe even in level 8 or 9, you are told Newton's laws, these, that. And exposure to mechanics is generally incomplete and to some extent misleading, and in my opinion, to some extent premature. When we were students, we are not given mechanics course in school. We have to go to college to learn. But nowadays, I find even the children, they are studying Newton's laws, solving problems with pulleys, these, that, laws. And there are neither frequent reference to the evolutionary nature of the basic concepts. In other words, the story of a physical to remains mostly unknown. Though we use it so much, like my egg curry. So evolution of dynamics is also one of the finest examples to demonstrate how science progresses. And understanding of that can remove many misconceptions from the minds of our young students who may not really know that how science is created or science progresses. And never also, this point I want to make here very clearly, never was the true nature of progress in scientific thought process better illustrated than in the following words of Lord Rutherford, the founder of nuclear physics. It is what he said: It is not in the nature of things for any one man to make a sudden violent discovery. Science goes step by step, and in every state, man depends on the work of his predecessors. Scientists are not dependent on the ideas of a single man, but on the combined wisdom of thousands of men, all thinking of the same problem, and each doing his little bit to add to the great structure of knowledge which is gradually being erected. So whether it is your Newtonian mechanics, whether it is relativistic mechanics, we give the credit to the last person who hawks all the limelight, but it is not their single-handed work. So if a student thinks, oh my God, I am not brilliant enough to sit below a tree and seeing an apple fall and discover gravitation, it is not the case. Nobody can do it and nobody did it. Actually, how it happened, that's what I also want to bring to the audience. But of course, many very large number of even eminent scientists really do not reveal this, They also pose as if they are the author of the whole thing. But so history of evolution of dynamics or Newtonian mechanics spans more than 2000 years, starting from the time of Aristotle to Newton. So it was 2000 years, and our students were saying, were they all stupid guys? They could not find out their physical phenomena. What is so great about it? But why it took 2000 years? So that is also very important for us to see. And very few of us are aware of the fact that some very fundamental questions on the basic nature of motion are still unresolved even today. That I may not be able to touch upon because of time limitation. But why it took so long to develop Newtonian mechanics? It should come to the mind of young students. They are very simple things, hardly any mathematics. There are a few reasons. They are all brilliant guys, and I will show you that what was their level of brilliance. There is a conspiracy on the part of nature to hide the true fundamental motion. Air resistance, friction, effects of Earth's gravity, all mixed together makes all terrestrial motions complex. And absence of accurate time measurement device was also another very important thing, because the key parameter was acceleration, second derivative, which is very difficult. Still we can recognize this. Acceleration is not so easy to recognize. And we need good, accurate time measurement devices. The absence of the concept of experimental verification of physical law. This cannot be understood by us in the 21st century. If philosophy was not there, if Aristotle has said this, why have to do experiment? It's true, gospel truth. Say like that heavier bodies fall faster. So here, say heavier so it will fall faster. So that was the kind of attitude people had, including the scientists. Missiles used to be considered to attain their high speed at the mid-flight. That is also a very standard thing. Objects need an impetus to continue motion. If something is moving, some impetus must be there to keep it moving. So if I throw a ball and it goes how? They used to think that there is a vacuum created because of its motion. Air goes and pushes, and that's how it continues moving. All kinds of funny stuff. And wrong philosophical ideas in religious establishments. I will not elaborate on this. You are all familiar with what happened to Giordano Bruno or Galileo or people like him, including our very ancient astronomer Aryabhatta, who wrote that Earth is spinning, and the kind of abuse and insult he had to, not he was dead, but all his subsequent astronomers used to always write that he was the biggest stupid person to write that. Anyhow, so these are the reasons why it took so long, and it is also very strange for us and to recognize at the very beginning that the key to the solution of the terrestrial motions was ultimately found in the heavens. Why it was so? Because celestial motions, heavenly motions, appear to be simpler. Every night it comes or it rises in the east, goes, and it is a uniform circular motion kind of thing. And it was there day after day, night after night for anyone to observe. So it was much easier to have observational science, using the heavens. Whereas here, you drop something quickly, it falls. I throw something, it goes and stops. I throw something like that, it goes in a curved way. It's an extremely complicated thing. So therefore, they started observing the heavens for studying motion. And again, you see, here also I'll tell you, and it is happening today, that that when the accuracy of measurement increases or improves by an order of magnitude, a new science comes. Either the old science is modified, or sometimes it is completely discarded, just as it happened with the special theory of relativity or even Newtonian mechanics. So when the accuracy of astronomical observations gradually improved, the scientists and philosophers came nearer to the truth. And you will see all major concepts, the concept of motion, concept of force, concept of inertia, everything came from astronomy. So in this presentation, an attempt will be made to unravel the story behind this conceptual evolution, the basic principles forming the foundations for Newtonian mechanics. The following points need to be emphasized at the very beginning. We must recognize this. Number one, it was impossible for all to conceive that interaction between bodies was possible without direct physical contact. Now, when I think I did one experiment in my native village using an absolutely illiterate person who never had gone to any school or anything, a poor person. So I asked him that I am dropping this stone, it is going falling. Why? So he thought and he said that because it is heavy. I said, what does it mean? Heavy? He said that because perhaps it has to go there, it wants to go. Then I realized it belongs there. That was the same thing which Aristotle said. So I think the two bodies can interact and do something and affect another one's position without touching. Was impossible. Even Galileo didn't believe it. The concept of force was also unknown. That force is an entity to cause motion was unknown. Motion was considered to be directly transferred. It is moving means I am moving my hand, and so along with my hand this is moving. That's all. But I am applying a force, and it is that force is responsible for it. That concept was totally absent. The concept of acceleration was unknown, and speed was the quantitative measure of all motions. And though it sounds strange, but the true science of terrestrial motions came from the study of heavens, and this is because I mentioned that heavenly motions are more permanent and somewhat more easy to quantify. Now the dawn, as I will not elaborate much, you all know about it, Aristotle's dynamics, and Aristotle at least was the first person to give a scientific or philosophical explanation to the motions. He said that motion means this wants to go to its natural place. So when I drop a stone, it goes to the earth because that is its natural place. And when I light a fire, it tries to flame and tries to go up because heaven is the natural place for fire. So that way he explained that why things move. But then somebody said that if I am throwing a stone upwards, it goes. Then he said that is not natural motion, that is violent motion. So he classified all the motions into two parts, natural motion and violent motion. And that was his science of motion. He also explained our universe, that means not heliocentric, a geocentric model, Earth is at the center of the universe, planets, the sun also considered one planet, they are all moving in pure, uniform circles. That was the law of motion. So then people ask that why it is happening so, what is the cause of their motion? Then Aristotle said that they are made of a different kind of material called fifth element. And this fifth element's natural motion was uniform circular. As you can, heavy body's natural motion is toward the center of the earth. A light object or plane's objective is to go up vertically as a natural motion. So fifth element is made of a different kind of material whose natural motion is uniform circular. That way the whole science of motion was explained. And it was functioning. And so therefore, actually what happens that when you find there are imperfections in your theory, then only science fails. Like as special theory of relativity or others happen. See, here also the same thing happened. How? It's very interesting. The first step was theoretical dynamics as a quantitative discipline based on observation was first happened in by Hipparchus in 135 BC. What happened actually? Now Greek astronomers were horrified when they observed the motion accurately. They found it is not uniform circular motion. And they said, how such a absolutely impossible thing can happen? They found that from 21st March to 21st December, sun goes, then 21st December to 21st September. So sorry, it is going this way. So 21st March to June, June to September. These are the two equinoctial points. These are the solstice points. So they are all 90 degrees. So it should take equal time. But I think they found that it is taking 94.5 days from that 90 degrees and 92.5 days for the rest. So therefore, they found it is a horrifying thing because it violates the philosophy of Aristotle. So then they tried to work, and the solution came by again Hipparchus. He was considered the first scientist to bring a solution to that. What he said that okay, Earth is not located at the center of the path along which sun is going, but it is slightly displaced. So it is moving in a uniform circular motion. That is the law which we must follow as an experiment. But I think from Earth it will look that it will look different because 90 degree and we are 90 degree. This will be more than 90 degree. This is less than 90 degree. So therefore, 21st March to 21st June, 21st June to 21st September, the angles are different when seen from the Earth. So that was the solution, and it was accepted by everybody because it saved the old science of Aristotle of uniform circular motion. This uniform circular motion played its important negative role till the time of Galileo, as you can see. The next difficulty was, of course, not for when more observations were coming. They were again found very serious problems with uniform circular motion. They found that the Mars moves smoothly, but then suddenly backtracks and again starts. So this retrograde motion, how is it possible with uniform circular motion? Again, a serious problem was faced by the scientists and philosophers, and solution came by Ptolemy. He said that they have to move in uniform circular motion, but there is not be one circle. So what happens? A planet moves in a circle uniformly. The center of that circle moves uniformly in another circle. He called this as the deferent and this as the epicycle. So then you can see, he explained that how we get retrograde motion. Say this planet is moving like this, and as the center of the epicycle is moving, so actual path of the planet will look to be like this. So two things could be said. That first of all, there are motions where for a short period it appears to move in the backward direction. And when it happens, then it is also, as found by the experiment, it was nearest to the Earth, and that looks the brightest. So this was the solution, and you see that it became a subject now, epicycle and deferent subject. Say, for example, there are many astronomers who will keep on fitting circle after circle after circle, because it is like a polynomial. You can fit any curve with number of terms. You could fit any observation. And there are perhaps many graduate students who fitted one extra epicycle to match a little bit of unexplained motion which you have observed. Somebody got some award also, I am sure. So that became the activity which continued for almost 1.5 millennia, not a short period. So don't underestimate the power of the kind of subject I am discussing. It is something like a laughing stock now, but that was the science for 1.5 millennia, 1500 years. Because with this model, you can fit all observations as it was improving to explain. But certain things could never be explained. But people ignored it. Generally, scientists, some of you are already scientists, some will be going to be scientists. The habit of scientists is that whenever something does not match, put it under the carpet. They are also the same thing they did. They could not explain that why the retrograde motion takes place only when a planet is in opposition. Opposition means what? That when Sun is and the planet is diametrically opposite with respect to the Earth. So when Sun is on the opposite side and the planet is just diametrically opposite, that position is called opposition. And when they are in the same line, in the same direction, it is called conjunction. So full moon is in opposition and new moon is conjunction. So the retrograde motion was always when the planet is in opposition. Because Sun is having its own circular motion, planet is having, why they have to have this kind of coordination? There is no logical reason. Now why a planet appears brightest when in opposition? If Sun is having independently circular motion, planet is having, so they have no relation to each other. Why this kind of relationship exists? And why the angular distance between the Sun and Venus cannot be more than that. It will be either seen as an evening star or as a morning star. You will never see the Venus above your head in the night. It is impossible. Why it is so? They could not explain. So now we come to the time when things started changing, and you can see it is the 15th century. It's almost 1,500 years have passed. During this period, only astronomical book available. I have gone through that book. I don't know any one of you have seen it. Ptolemy's Almagest. And really he was not a very revolutionary person, because he believed in the principle of uniform circular motion more strongly. He tried to explain everything with the help of only one circle rather than cycle and epicycle. He said it should be possible. And then, as he himself writes, that he was trying to explain everything with the help of uniform circular motion, because that has to be the divine rule of absolute motion. And he was referring to the past literature, and found that in the very ancient time there were propositions which said that Sun is stationary, Earth is moving. You know, Aristarchus in the 4th century BC, perhaps, or 5th century BC, he first told that Earth is rotating about the Sun along with the planets. And so he saw that, and he said that, okay, why not try with the Arachne model? So he found that he could explain the retrograde motion and all things with this heliocentric model.
I think you have to push it hard, I think.
We have one of these.
This is the receptor or you have the opposite.
Yes. Anyway, you see, I cannot move from this place because I am prohibited doing so because excuse me. You see that we can explain that when this is the planet of Mars orbit, sometimes it is coming.
I think the battery may be very low, so we have to press for a little while anyway.
So you can see Earth is going like this at a faster rate, Mars is going like this in a circular motion, slower rate, and this is a Jupiter or say fixed stars, the heavenly fixed stars which frames the background against which the planetary motions are seen. Now you can easily show that when Earth is here, Mars is here, it will appear to be there. When it is here, it will appear to be there. When it is here, Mars will appear to be there. So here you can easily show, which Copernicus did, that retrograde motion he explained with the help of uniform circular motion, but it has to be about the Sun. He could also explain that why the retrograde motion takes place when the planet is in opposition. That means Sun is here, Earth is here, planet is here. He could also explain that since in opposition a planet is nearest to Earth, it will appear to be brightest. The distance is there. All the things he could explain. But he said, and he also explained why the Venus is never seen beyond a particular angular distance from Sun. Because if this is the orbit of the Venus, this is Earth endpoint, then the maximum angular distance of Venus from the Sun would be the angle made by the tangent to this side. So everything got explained, but he was very afraid So he didn't allow his book to be published. The book was published only he was dying. He was given a copy there, The Revolution of Books. And he only said that this is not I am proposing to be what is actually happening, but you can explain with this model the kind of things you observe. You are very clever to avoid the onslaught of charge. He never said that the real thing is happening. So after 1500 years, we get a proposition by Copernicus that it is the sun which is there, not at the center, but the planets are moving and this is stationary. And in case of Ptolemy and previous astronomers, Earth was the stationary and the other things are. Then there was a gentleman called Tycho Brahe, perhaps you have heard of him. He was a real tyrant and his obsession was with accuracy. With naked eye astronomy, the accuracy of angle with which he could measure, it was only 2 minutes apart. And he collected 20 years of data at Uraniborg in this observatory. And the good thing was that he had assistant, the German mathematician Johannes Kepler. So a very happy and fortunate incident happened that Tycho Brahe died, in a banquet with the king where he was drinking, but the courtesy prevented him from going to the washroom and to relieve him. So ultimately what happened is urinary bladder burst and he had a painful death. And that was a great thing to happen for science. Because Tycho Brahe wanted all his data, huge amount of accurate data, must be used to prove Tycho Brahe's model of the universe, which said that Earth is at the center, Sun is moving around the Earth, and other planets are moving around the Sun. Now, kinematically, interestingly, you are all in mechanical engineering, you could explain the observation with anyone, because it is only the relative positions you are. So he said that this must be a theory, and all my assistants must prove that it is the Tycho Brahe model which can Oh, you went for that. Thank you. Thank you very much. Yeah. So this was the, but he died. So when he died, one thing I must tell you, maybe I am taking a little bit more time. So if you take it like a story, I think you'll bear with me. So his assistant, somebody took the furniture, and somebody took some steel things or some glass-made things, somebody took curtains of the windows. What Johannes Kepler did, he took all the records of 20 years and he started studying. He could fit everything with Tycho Brahe or Copernicus or Ptolemaic model. Only thing he could not match was 8 minutes of arc, that distance of Mars's orbit. He could never do. And he was not satisfied. He did a lot of work, and only thing what he found that you can explain it correctly, accurately, if you assume the orbits to be filled, not such. So first time in history that you were freed from the cycles of uniform circular motion, and he said that they are moving in ellipse with sun at the focus. How he found it was also very interesting. What he did, I will come to these things, a lot of things he did. So what he found that they are all ellipses, and actually they are not in same plane. So the one plane in which Earth moves is called the plane of the ecliptic, and all other orbits are slightly deviated. And he found out that the line of apsides, that means where it intersects, this orbit intersects the plane of the orbit of the Earth, ecliptic, these are the points of the line of apsides. When you add that, or you join all the major axes, they pass through one single point. And he also found, very strangely, that point is occupied by the sun. So he was convinced then the sun must have something to do with this motion of the planets. It cannot be just sitting idle there. Earlier, sun was not exactly sitting in the center, somewhere there. That's all. Or Earth is sitting somewhere there. But here is the first time that Kepler came with the idea of interaction between two bodies which are at a distance. One is sun, one is sky. Now here I will slightly digress to tell that all those old philosophers and scientists were not stupid people. Instead, they are gigantic intellectuals. Now I see that what Einstein said, it is rarely discussed, but it is a very interesting point. And it is worth appreciating how difficult the problem was. How Kepler found out the orbits of the planets. Now you see, you are sitting on Earth whose motion is not known, orbit is not known. You are observing another planet whose orbit is not known. Only thing which can be done in astronomy is the direction in which you can see, nothing else. You cannot find out its position. So it's only that data that which direction a planet is, sitting on a body like Earth which is moving and motion is not known, and finding the orbit of another object is extremely difficult, and that's what Einstein said. To grasp how difficult a business it was, needing to find out the actual rotating movements, one has to realize the following. One can never see where a planet really is at any given moment, but only in what direction it can be seen, just then from Earth, which is itself moving in an unknown manner around the sun. Difficulties thus seem practically insurmountable. Kepler had to discover a way of bringing order into this chaos. To start with, he saw that it was necessary to try and find out about the motion of the Earth itself. How he did it? Now I don't know, have any one of you ever come to this point that how Kepler found out Earth's orbit or planetary orbits? What I did when I used to offer this course as an elective, I used to give this as an assignment. I said, you are gigantic intellectuals compared to what Kepler was 400 years back. You know so much of mathematics, so much of geometry, so much of calculus, so many things. Tell me the way you propose to find out the orbit of the planet with a system where you can see a planet in a particular direction. I said, I am giving you the whole semester. Anybody who brings it, I will give you a straight A without any examination. So for 5 years or 6 years, I offered this course. Nobody could do it. They tried because they found it an extremely challenging thing. So the scheme was like this. You see, Kepler first knew that the orbital time of Mars is 1.88 times the orbital period of the Earth. The orbital period of the Earth is 1 year, it was 1.88 years. So he considered that instant when Earth, Sun and Mars was in opposition. Starting. Then after 1 year, what happens? No, sorry, this was the position. And after, this was the position. After 1 year, Mars year, 1.88 years, Mars came back to the same location, but Earth completed one and another little bit and came here. So therefore, after 1 Mars year, his configuration will be like this. He could measure this angle and he could measure this angle. So therefore, he had this line and these two angles. Then after another 1.88 years, Mars was again same position and Earth was somewhere here. So he again measured these angles. Only angles could be measured. So this way, he could, with triangulation, he could really find out the relatively, if you do some scale, if you put it here, and you can get the positions of the Earth like this. And that way, first the orbit of the Earth was determined. Once Earth's position was determined, the same thing was done on the Mars, and the Mars orbit was found. It took decades of time, calculation, because in those days they didn't have calculators, computers, even log tables. So when the log table was first discovered, somebody told that that fellow has increased the lifespan of the astronomer by a factor of 2, because the amount of work we could do with log tables was double the amount of work which they could do it in the earlier time. You have to these 8 decimal places, you have to multiply and manipulate, very difficult. So what you see now, Kepler's model of the universe, you all know that the sun is at the focus of all the ellipses which are being followed by the planets. That is the modern theory. Now and here he told that sun must be causing the planets to move, and concept of force as an interaction between bodies to cause motion was first given by Kepler, and that is the first definition of force. So you can see also that Kepler also had a scientific idea of the gravitational interaction between two bodies, not in physical contact. It is clear from the following statement in Astronomia Nova, his book. You can see what he writes. It is his, I am quoting. Gravity is a mutual propensity between the like bodies of to unite or come together, so that the earth draws the stone to it much rather than the stone seeks the earth. If two stones were to be placed anywhere in the world outside the range of influence of a third similar body, then each stone, like two magnetic bodies, would come together at an intermediate point, each stone traveling towards the other a distance proportional to the bulk of the. It is almost the law of gravitation by Newton, and it was by Kepler long back, to the century. So he also conceptualized an entity like force, which was completely absent before that. Nowhere you will find force. They only got impetus, etc. Air is pushing behind the arrow, so arrow is moving, that kind of very rudimentary concept. Of course, he was unaware of the fact that acceleration and not speed depended on force. So all his model of the planetary system, he tried to see that the force and velocity or speed is proportional, so it didn't work. But he also was the first scientist to conceive the idea of inertia of rest. Unless you do anything or apply any force, it will not move. And he said that term inertia also was coined by Kepler. So what he did, you know, I will not go into the details. Planets move in elliptic orbits with Sun at one of the foci. With the Sun at the origin, the position vector of the planet traces out equal areas in equal times. You have read it in school, the second law. And if t be the time taken for planet to complete one orbit, and 2a is the major axis of its orbit, then the third law, that t square by 8 is constant. With Kepler's law, celestial mechanics became released from its millennium-old shackle of purely geometric character. It became a dynamic system. Earlier planets were moving around geometric points. Now they are found to move around material body like Sun. And the foundation stone of dynamics was thus laid by Kepler. Now, concept of acceleration was there much before. It is not true that Galileo was the inventor of the concept of acceleration. In Oxford, in the 14th century, they studied accelerated change, not only of position but also temperature, coloring, everything. So there they also had accelerated motion, uniform acceleration, and they also had this law: s is equal to half at square, which we use in school problems, and it was known as Newton. It was in the 14th century. But I will not go. There are many people came in doing a lot of research, but I will come to Galileo. He was the person who studied free fall very accurately and had that mathematically developed that relation s is equal to half t square. He knew that any uniform accelerated motion, the distance traveled increases as the square of the time. He also had the idea of combining motion. If I throw something, it will have uniform motion and also accelerated motion, so it will be parallel. He also thought about a thought experiment that if I drop a stone through a smooth plane, it will come down, and if it goes up another plane, it will go to the same height. So he started thinking that if the inclination of the other side is less and less, where it will go? You can see it will go farther down. And if it is horizontal, he said it will go continuously. So the first law of motion in a slightly distorted form. He said that if you move something, it will move in a circle around the earth. That was his law of inertia, which is somewhat incorrect, but at least he could get the idea that it will be an unstopped motion continuing. Only thing, instead of going in a circle, in a straight line, it will go in a circle. Projectile motion he did, and crude form of inertia of motion he did, And he, of course, astronomical discussions were there, moons of Jupiter, phases of Venus. That's how his conviction in Copernican model became completely firmly, and in his teaching also it was there. That's how he had the problem in the church. He also had the sunspots and found out the rotation of the sun. And he said that if the sun is rotating, the planet is, they are also rotating, something like a sweeping the planets around that. But in spite of all these things, he was also the last tenant of the old edifice of the science of motion. And the destruction to that old building came to Rene Descartes. This was Galileo's wing. One was the free fall study, inertia of circular motion, and composition of motion. The Rene Descartes was the first person to come with the fundamental, most difficult law of motion is not the second one, but the first one. That something moves in a straight line. Why it is so? Because there is no uniform rectilinear motion in the universe. If you drop something, it goes in a straight line, but it is not uniform motion. If you throw something, it goes in a straight line, but it is not uniform motion. And if you throw something like it, it doesn't go in a straight line. So there is no uniform straight line motion defined. But it was difficult for the scientists to think that that is the fundamental motion of mechanics. So it is Rene Descartes who gave the first law of motion in its correct form. He was doing experiment with slings. When the string breaks, he noticed that the stone goes in a straight line in the tangential direction. His friend and student, Christian Huygens, did very important things. He derived the conservation of momentum principle, conservation of energy in a rudimentary form, and correct expression for the centripetal acceleration using circular motion, which played a very important role in discovering the inverse square law of gravitation, as you will see. And he also established, which is the most important thing, that acceleration is related to force, and they are linearly dependent. How he did it? He was doing experiment. When he hands a body, he finds there is a tug. Force used to be called as tug. He measured the tug. Then if it is an inclined plane, the tug was little less. When it is in a body like this, the tug is same as this. It doesn't depend on what was happening. So he was finding that this tug, what it is doing, it is preventing this to accelerate in this direction. What this tug is doing is preventing its acceleration in this direction. What this is doing, preventing its instantaneous acceleration at this direction. So he said that if it prevents that acceleration, if a tug is applied in the opposite direction, it will cause that acceleration. And that's how he came with this. The tug is proportional to acceleration. That means if a force, which is actually nothing but something like that, when it is applied, it will be proportional to acceleration. That is the real basic breakthrough in mechanics. This time, acceleration and force, they are being related, which was quantified by Newton later. But Huygens' next very important was the expression for the centripetal acceleration, omega square r, which you know that, or v square by r. So this was used by Robert Hooke and Edmund Halley to prove that the gravitational attraction is an inverse square law. That was also not done by Newton. So I will not actually what he did. He said that if something goes in a uniform rectilinear motion, it's left undisturbed, and same particle when moves in a circle, it will go here, here, and here, instead of going to this place, this place, this place. So he found that this distance is nothing but a fall towards the center. And he could easily, you can also easily do it by geometry. He showed that the fall is proportional to the square of the time it is taking. And so it must be a uniform acceleration towards the center. And he actually, I will not go into that, he said that the acceleration towards the center of the body, which is moving with a velocity v, is v square by r. And of course, the tug is equal to m omega square r. He also found out by this experiment. He hung some body and rotated that body on a horizontal smooth table, and he found that this m, the bulk, he didn't have the concept of m, into omega square r, and this bulk, they are proportional. So, as the expression for centripetal acceleration was determined, it could be shown using sling experiment and also the table experiment that the torque is proportional to acceleration. And this was the most important breakthrough for deriving the law by Newton. What Newton did, that the bulk of the matter he defined by a quantity mass, which is very important. And so therefore the framing of the second law was by using planetary motion analysis, and the demonstration of universal gravitation's inverse square property was also by his centripetal acceleration model. So you can see that if it is a movie in a circle, it forces with the attraction, and you can find out the acceleration according to Huygens formula, and you can easily by a simple high school algebra you can show that this force is inversely proportional to r using the Kepler's third law. So did anybody else gain from the deep insight developed by Huygens? You see that Huygens and Galileo both failed to claim the greatest prize. It would have been even 10 Nobel Prizes, though he came very near to the grand synthesis. But Galileo, again, Huygens was totally opposed to any idea of interaction of bodies at a distance. He didn't believe in a kind of force like gravity. I don't know why. Because magnetism was already known in that time, and magnets attracted, that was known. Actually, Kepler was influenced by magnets, and that's how he came with his idea of gravity. Newton accepted Kepler's idea, and using Huygens' formula, which was derived when Newton was a small boy, he derived the formula. And Newton also showed that the apple which falls, the acceleration, and the moon is also nothing but a continuously falling body. Any orbital motion is that. It goes little bit, it falls. Again it goes little bit, it falls. But the surface of the earth also is curving, so therefore it never touches the attractive earth. So this is basically what happens. So moon is going in an orbit means moon is falling towards the earth. So he found that the same force is responsible for the fall of the apple and fall of the moon. That's why Newton used the term universal gravitation, not simple gravitation. Earlier, it was not conceived that the same laws of physics are valid on the terrestrial surface, also in the heaven. That was the first time he spoke. And of course, he did one thing in the last thing I showed, that he proved mathematically that if an object goes in an elliptic path around a central body, the force of attraction is inversely proportional, or vice versa. This nobody could do. So you see, I will not go through the book, it's very interesting. I have left the whole thing with you, and I think if some student is interested, he can use this. He had his ellipse, and this was a focus, which is the sun, for example. One thing he did, which only Newton could do, he first derived this property of ellipse, that this x, where is x? X and y. X is the line which you get drawing a tangent from point P, and this is a line which is parallel to the line which is joined from point P to the focus. So this is xy. And AB, PQ is this, YZ is this, XL is this, and that way XL is this, KL is this, XI, X is this, and I is there. So this property he first proved geometrically. And then here I have given this simple derivation by which you can show that this distance and this distance, they are proportional to the square of the distance inverse. So since this is nothing but a fall with the acceleration, this is nothing but the fall of acceleration at this point, and this is nothing but a fall at this point acceleration. So accelerations are proportional to this fall, and that he showed was proportional, inversely proportional to this distance. So therefore he showed that the force which is attracting the planet here is inversely proportional and it produces electric motion. It was not the calculus based proof. These days we do it in college and school. So all those days were based on geometry and based on proportionality. All proofs you will see the old. And that is why, though the book is most referred as Principia, it is the least read. It's so difficult to read, you will not touch it after 10 pages. So the whole dynamics, and of course Newton had one original law of motion that was purely his, and without which dynamics could not develop. That is the third law. Third law has two forms. One is weak form, which says that the action and the reaction are equal and opposite. And the strong form of third law says that the action and reaction, they are equal and opposite and acts along the same line. They are two different, slightly different. In some cases weak form is there, and in most cases of course we have a strong form. This is 100% Newton's creation, and that completed the dynamics, because without third law you will not be able to solve any problem you see. Whether it is impact problem, collision problem, any kind of thing. You always put that, oh this is this, so that's another minus it. Without that the mathematical formulation cannot. So I think who else had made still further use of Huygens insight? Huygens showed that acceleration and gravitational pull, they are equivalent. One is supporting another. Now you see this experiment. So it is after 2.5 centuries Einstein did this, and he developed his general theory of relativity by showing or using the equivalence of gravity and acceleration. But what happens? What general theory of relativity says that an object in near a gravitating big body, it follows the geodesy, the natural path. So we come back to Aristotle now. That bodies are falling because that is their natural path. That is what ultimately Einstein's general theory of relativity proves. It should be remembered that all the derivations and analysis were in geometric form, and the modern differential form of dynamics which we use is a much later work, and primarily contribution came from Bernoulli, Euler, and others. Then other branches developed, like Leibniz started the analytical mechanics and all such things. I will not go through, but the science of motion was finally established with the 3 laws of motion. First one by René Descartes, second jointly by Huygens and Newton, and third by Newton. Thank you.
Thank you. Thank you, Pavel, for a very entertaining and enlightening talk. So I hope that you will take some questions.
Yes, definitely.
Are there any questions?
Now you have learned nothing new in this. We are just discussing the story of A is equal to mn, which you learned in school. But what happens here, that a book science, A is equal to mn, we have done. But exactly the concept of force, the concept of motion, instantaneous motion, kinematics, quantities, these things we don't think in a very deep way unless you have seen that how painstakingly the history has taken the scientists and philosophers along the path. So that's what I want to tell, that if you go through the whole process, then you will realize, and also go through their derivations, geometric derivations, but their derivations. I can tell you that your complete grasp on the subject will be far more complex and strong. So go through their derivations, their proofs, not today's simple d2i, d2 dx, d2a, d2 m is equal to x. No, that will not be the real physical field. Because they were ancient scientists, they had to work with their real physical field.
I'll ask you a question.
Can I sit here?
Please do. Of course, Ghosh has a little problem with his seat, so. Yeah, of course, it's known that Newton's law of gravitation, inverse square law, that was based on Kepler's observation. You try to fit it
And
basically third law,
and
second law also.
And centripetal acceleration is formula by Huygens.
But I want to ask you one thing. Did Newton, do you know whether Newton tried some other forms of laws of gravitation, not inverse square law, but maybe 1 by R cubed or anything like that, before he came up with his inverse square law?
Newton did something like that without much serious interest, but subsequently in the 19th century astronomers did it. When they found that that any gravitating object will have a closed orbit like an ellipse only if the law of attraction is perfectly inverse square. But they found the Mercury's perihelion is advanced. That means it is not a closed orbit, it is going like this. So they tried with various kinds of form like 1 by r to the power 2.00001, all these kinds of things, but they are all very ad hoc assumptions. But Newton also had some study that what will happen if the law is not exactly 1 square. But since it was not calculus based, so not much progress was done. But he did something.
Because of course he did a lot of geometry, but he also invented calculus, which was sort of geometry, but
that calculus was
basically tangents. That based on tangents and so on. It is geometry in a slightly different sense.
I'm saying, it is not there anymore. I'm saying all these drawing actions by drawing, or even your Huygens that derivation, they're all considered to be happening with a very small spot near that point. It was only an exaggerated figure. So that is always there, that it is happening at a very small narrow zone where we are considering. So that is true, and that is the basic thing of calculus. But they are all geometry.
Because
so
when Halley, asked him,
he asked that, if the inverse square law of gravitation works, then what will be the orbit? He said ellipse. He said, can you prove it? He said, yes, I have done it somewhere. I have misplaced the paper. People don't believe it because that derivation will be the height of achievement in that time, and somebody will misplace it is not acceptable. So he thought, but he worked later and it took long time. Even that universal gravitation, to prove that apple and the moon, they are being same law of motion, but he had to wait for 10 years to publish that. The reason was to find out the distance between moon and earth was not very difficult. There is this much. But what is the distance between apple and earth? Apple is here. Is this the distance? So it took him 10 years to prove that for a spherical body, center of attraction will be center of the sphere. After he did it, then only he published his result, where he took the distance of the apple from the distance from the center of the apple. So he had to prove it, and it took 10 years.
A comment and a question. Apples to the contrary. Didn't it take 21 years from the time the apple supposedly fell on his head to the time he published the Principia Mathematica?
Yeah.
So there must have been a lot of work involved.
Yeah.
The question is more interesting. The concept of perfectly circular motion and the concept of the Earth being the center of
not center, somewhere near the center.
No, the epicycles come, the Ptolemy.
And the center of the universe was Earth center.
Yes, it goes back to Aristotle. But are there other traditions, and I'm thinking of the Hindu astronomers and so on, who also believe that all the planets revolve around the Earth, or were there other astronomers who believe that the Earth itself moves?
Only one reference in 4th century BC by Aristarchus. Nobody else.
But Aristarchus is supposed to...
Aristarchus, he said that the planets are moving around the sun.
Exactly.
And sun is at the center.
And the reason for the Earth-centric view was also partly religious, was it not?
No, Earth-centric view, you want to know why. People didn't have the concept of inertia of motion. They thought that if I am throwing a stone up, by the time it falls, Earth has rotated. So it should fall at a different location. They didn't have the concept of inertia. Aryabhatta, in the 5th century AD, he wrote about the daily rotation of the earth as actually the motion of the heavens. But he was abused by all his subsequent astronomers. Say absolutely stupid remark. How can you think that Earth is rotating?
Any other question?
I think the students should ask question because whole lecture was primarily meant for them. But I think any one of you, I think I will not suggest that you go and read Principia. It will be tremendous, apparently wastage of time. But many of the derivations what they did, like say Kepler's way of finding out the orbit of the Earth and orbit of the planets, then Huygens' derivation of the centripetal acceleration is v squared by r. Then second law of Kepler and third law of Kepler combined with centripetal acceleration formula by the inverse square law. These are some very basic fundamental things, you know. And if you do these derivations once again, the concept of those quantities will be much stronger.
Well, there is a question.
Sorry. So when you say like that, for example, like Ethan was talking about like F is equal to ma, what was your concept like of acceleration? If I'm not mistaken, Leibniz was the first like to come with a, let's say, a nice form of differential. Sorry. What was their concept of acceleration?
That is in the 4th century AD.
Sorry.
It was in Oxford.
But I mean, like the simple form of like.
Oh, that was also the I'm telling you, Newton School developed formula for finding out the change when it is an accelerated change. Only thing that they did it for everything, any change in the temperature, change in color. If it is an accelerated change, the total amount of change will be halfway. That they did, and it was applied to motion, that is kinetics, by Galileo. He again did all those experiments. He did one good thing, very clever thing, because vertical motions are very quick and you don't have such a clock to measure such a variation. So he did experiment on inclined planes, which effectively reduced the gravitational acceleration as g cosine theta or sine theta, whatever. So that way he had groups connected, and whenever the roller crosses a group, it will give a sound. Okay. So that was the kind of experiment. When what he did, he marked wherever the pendulum clock he had, at same time he marked, and later he found that these distances are actually increasing square. Because time was constant for each, it was going square. That the application of this accelerated change applied to only motion parameter was by Galileo, obviously, and he did that. But even Galileo really didn't work much on force and acceleration relationship. That was much later. Okay.
Any other questions or comments?
Yeah, please.
During the lecture, you said that the scientists' studies of dynamics were stuck in sort of a rut of the paradigm of epicycles for a very long time. Would you care to suggest any reason why they would get stuck, or were they just not creative, or were they just?
Well, I'm telling you, first of all, you see that in science, and you are going to be a scientist in Cornell, you will also perhaps have sometimes that attitude. If you can explain some observation, you will think that what I have done. Okay. So with those models, they could explain the observations. But they thought it must be correct. There is no reason to believe that it is not correct. Only as more and more difficulties were faced, then things were changed. Ultimately, it was discovered. So initially it was uniform circular motion, then the uniform circular motion with slightly displaced arc position from the center, then that along with some epicycles, and that along with some epicycle over epicycle over epicycle. It is nothing but a polynomial solution to a function. So they managed it, they could have it. Their objective was what? Astronomical, positional astronomy. So to find out the position of some planet and the moon, etc. Because why they did it, they are all astrologers. Even Kepler was the astrologer. Because king will pay you something Only when you can tell that if you start your war with neighbor of that and that date, you will win. He is not bothered about whether sun is going down the earth or earth is going down the sun. He has his. So, to develop credibility, that yes, my predictions are correct, they have to make some predictions over time. Like say, okay, such and such time and such date, you will have an eclipse. And then people wait and find, yes, it happens. Then they will believe that what you say it happens.
Okay, thank you very much.
Thank you. Thank you.